Evet, resimle başlayacaktık değil mi? This is just a picture of what we covered last time. If you just imagine yourself being on the network at point Vs, and what I have here is not an edge, but it's just a path beginning at Vs and extending towards other parts of the network. Okay? Of course, there are several such paths, but I can't draw all of them. And this is another path, just extended to other parts of the network. What happens is, if you pick, for example, some other vertex Vi at another part of the network, and if you start plotting the weighted distance from Vi, then as you move away from Vi along a path towards Vs, assume this is the shortest path between Vi and Vs. So when you start moving on this path from Vi towards Vs, of course, you are increasing the distance. This is the plot of the distance from x to Vi plus Ai. That's the plot of that. Now, the height of this is Ai. You're imagining there's a vertical axis here, which actually supplies the values of the weighted distance plus the addend. So you might want to just imagine there's a vertical axis there. So at the point x is x being equal to Vi, the distance is simply 0, in which case you've got Ai, and that's that height along this axis. And as you move away from Vi along this path, of course, this increases with a slope of Wi, just like that. Okay? So it just goes like this. And finally, it gets to wherever it gets to here. It will continue like that. Okay? And it also goes the other way also with a slope of Wi again, relative to moving away from Vi. And now if you do the same thing for Vs, at the point Vs, we assumed that this is the largest of the, in other words, we found out that f value at Vs is equal to As, which is the largest of the Aij's. Alpha ij's, sorry. Okay, that was the situation. So at that point, the value of f is at a really higher value, and it has its own Ws. This is the same plot that you see here. It's the V type of function, except that it's relative to Vs now. You begin at Vs and you start moving. So this is the plot of that function. And it goes this way. And the reason I drew it this way is because at the point the first one reaches here, it's below that. It doesn't exceed that. This beats everybody. This picture is true for every vertex Vi. For that reason, the value of the function here is defined by the height As. Okay? That's what we've got. And you can see here that since this is true for every other vertex Vi, as soon as you start moving away from vertex Vs, you're actually increasing the f function. There's a local minimum here whose value is As. As soon as you start moving away from that, you start increasing that. In fact, we use that information in the proof. Okay. For that reason, this is the unique minimizer. In this case. Now, what happens when you have the following? Wn in this case is greater than Ai for all I. So let's assume this is the situation. In the former case, Wn was defined by this relationship. In fact, this was equality because Wn is always greater or equal each of these Ai's anyways. So the reverse inequality would imply equality. So in this case, you have strict inequality, in which case, of course, if you've got your Vs here, and if you've got your Vi here, it has something of this nature, and this one goes like this. This one has its own, such as that one. You've got other V type of functions just extending every which way, and it turns out that whichever one happens to be maximum here, that defines the value of the f function. So in this case, of course, a particular Vs, a particular vertex such as this one will not be a minimizer. Rather, the minimum will be defined by the intersection of some V curve with another V type of function. This is just an intuitive way of thinking about this. So let me state that as a formal property here. Let x bar minimize f and assume Wn is greater than Ai for every I. And there exists there exists a pair of distinct vertices. Distinct means different, right? Distinct vertices Vs and Vt such that the value of f at x bar, that's the minimum value, is equal to the weighted distance Ws dx bar Vs plus As, which is also equal to Wt distance between x bar and Vt plus At. So that's the intersection point I'm talking about. One is coming from Vs, the other one is coming from some such Vi, which happens to be, in my case, in the property T, index T. Okay? I'm not going to give you a very formal proof of this because the formal proof requires a bit work here, 2 pages, but I'll just give you the intuitive idea behind it, and that should be sufficient for the proof. By definition of the function f, there exists a node or a vertex Vs such that the value of f is defined by that particular weighted distance. F of x is the maximum of weighted distances plus the addends, so it should be realized by some index s. Okay, that's all. And we know that this is greater or equal wi dx bar vi plus ai for every vertex index I. S is already included, so let's just separate S out. Okay. Now, if you happen to have equality here for one index, you're done. The proof is just completed. So the more difficult case is what happens if everybody is strict inequality here. Okay? So if the inequality is strict for all I different from S, then what do you think would happen in that case? If you just think of this picture.
Move closer to S, and this will decrease the...
Exactly. Yeah. Then you can move, let me just illustrate that pictorially here. So we know that f of x bar is equal to ws dx bar vs plus as by assumption. Okay? And if this guy is strictly greater than every other function that reaches here, none of them are better, okay? In that case, of course, you can move here slightly towards Vs, that's what John is saying, and get better or get smaller in the f value, okay? That's the idea. So, then we can find a point x along the shortest path connecting x bar to Vs such that x is closer. Closer means strictly closer. Okay, x is closer to Vs than x bar, and that f of x f of x bar is greater than f of x. Why? Because when everybody is inequality here, a slight movement from x bar towards Vs, just a small movement, will make this distance shorter, but it will not be too short. In other words, it will not get too so that f of x bar will be, in this case, greater than this weighted distance when x bar is replaced by x. And of course, because we had strict inequality, I can keep x so close to x bar that all of the inequalities that we had here can still be preserved, that they wouldn't be switched, so that the value of f would still be defined by this particular weighted distance. Okay, that's the idea. If you got that idea, and of course it's a matter of writing it down, which I cut it short here because it's just you need to go into the epsilon arguments and use the continuity of the functions under consideration and so forth, which just makes it a 2-page long proof. But I don't think you need that at this point, okay? It's just technical way of writing it. So let's just suffice to conclude it here. Some of these things are like this. When you have strict inequalities, then there's a little ball around the point under consideration, which means that as long as that ball is small enough, any movement in that ball will keep all the inequalities the way they are. They won't be reversed, in which case you can make such conclusions. Okay, so that's a general idea for many types of proofs. Okay, I'm going to conclude this here, and I'm going to now start talking about tree network problems for center location. Okay. So let's suppose that we have the same function, f of x. This time x is varied in a tree network, an embedded, connected network with no cycles, where f of x is again defined by the maximum of the weighted distances plus addends. Let's assume we have n vertices under consideration. So let's look at a very special case now. Each weight is 1 and the addends are 0. So in this case, you're trying to find a point in the tree such that the vertex that's farthest away from the point under consideration is as close to it as possible. Okay? Here's an example. I always seem to draw the same type of tree, but nevertheless, I guess you can live with that. Let's just assign some numbers to the edges. Let's make this one, for example, 5, 5, 6, 3, 2, 2, and let's make this one also 3. Where do you think is the minimizer in this problem when all vertex weights are 1 and addends are 0? Anybody?
In the middle of this.
This one? The middle of that one. Right here. X bar, for example, is the minimizer. Why? Because when you're here, you have a distance of 3 here plus 5, which is 8. And then you have also 3 plus 3, which is 6, plus 2 is 8. So you have 8 both ways. If you move to the right slightly to get better with relative to either that one or that one, then you would be moving away from that, so your f value would be increasing. Same way if you move to the left. So obviously that is in fact the unique minimizer in this case. Okay. All right. So what do you see in this example? You see in this example that the minimizing point happens to be the midpoint of a longest path in the tree. There's this path whose length is twice it's 16. And you could have also gone this way, it would still be 16. There could be other alternative paths, but each would be intersecting, or the midpoint of all such paths would be intersecting at the same point, which is interesting. Well, tree networks are, of course, very special. When you have no cycles, that means to go from any point in the network to any other point in the network, there's exactly one path to go along, and that path will be the shortest path. So shortest paths and all paths between a pair of points are always the same. There's only one. And so that gives a very special feature to this. So in this case, X bar, which is the optimum of this, the absolute center, is the midpoint of any longest path in the tree connecting some two vertices. Okay. It's true for all tree networks. I'm not going to prove it, but all you're trying to do is, when you look at this problem, in this special case, you're trying to minimize z subject to distance between x and vi being less than or equal to z for all I. That's all you're doing, okay? Because minimizing f of x x and t is the same as minimizing a number z where f of x is bounded above by z. That's a standard trick. Well, it's not a trick, it's just a straightforward way of handling an optimization, a combinatorial optimization problem in a slightly different way by introducing an additional auxiliary variable. So you're trying to push this variable z down as much as possible, but you won't be able to push it further than you can minimize f of x, okay? And that would be the same as minimizing z, f of x is the largest of distances. So since z will be greater or equal the largest of such distances, it will be greater or equal each such distance. That's why I've got every distance being less or equal z. Those two are equivalent. Okay? Now, what's the use of this? The use of this is the following. If you look at your tree network, whatever it is, let's just look at the previous one with the same lengths. I'm not going to put down the numbers, but let's just assume those are the lengths. Now, if I happen to pick, for example, z to be, say, 10, or whatever, just pick a number. It doesn't have to be greater than 8, which is the smallest number. Let's pick 10. Now, if I, for example, place myself here as a tentative location for my center, I want the distance between the point under consideration and every vertex to be less or equal 10. Well, when you go this way, this is a distance of, 5. So moving along this direction will certainly satisfy the constraint relative to that particular vertex. Moving along this vertex will certainly satisfy the constraint because, again, the length is less than 10. When you start moving along this way, you will get as far as here, 6. You can go 4 more units. Now, this one was how much? 3. So I can go all the way here, 3. And I can go 1 unit up to the middle of this edge and 1 unit up to the middle of that one, right? So 6 plus 3, 9, 10. So every point in the cross-hatched portion of the tree would be within a distance of 10 units of x. Okay? We're trying to cover every vertex. Of course, I did not reach these two. So that choice of z and this choice of x did not do the job because that particular vertex is not within 10 units of this point. Also, let's just complete the picture. This one is also included here. Okay? So what you're trying to do is, for fixed value of z, you're trying to find a point x in the tree such that the cross-hatched tree network, which includes every point in the tree within the upper bound picked at the point, picked at that moment, that subtree should include all the vertices. In this case, that particular choice is not a good choice because it did not include these two. However, you can see immediately that if you move x to a new point, which is, for example, 1 unit here, just moving it 1 unit would be enough. So if I pick y, for example, 1 unit away from the other one, then my cross-hatched tree network consisting of all points in the tree for which x and y less than or equal to distance between x and y is less than or equal to the upper bound z, then in that case, this would also include these as well as that. So in that case, that would be a feasible solution. Okay? So in this case, at point y, this set of points is the same as your tree network. Okay? It includes everybody. Now, so the question is, well, can I change to a new point, say U, which actually satisfies this with a something smaller? So, for example, with 8 or with 9. That's the idea. Now, that's the viewpoint when you start looking at this problem from the point you're trying to place. In other words, right now your viewpoint is you place yourself on top of the candidate point for the center, and you find or construct a subtree whose radius is whatever value you pick for z. Does everybody see that? You're trying to simply find a subtree whose center is at the point you pick and whose radius is as much as the value you pick for z. That's one viewpoint. Now, the other viewpoint is by looking at it from the viewpoint of vi. So the constraint, well, the distance is symmetric. The constraint simply says that if I fix I, for example, to vertex number 1, suppose that's your vertex number 1. Let me draw it here. When you look at this constraint for vertex 1 alone and with a picked value for the upper bound, this simply says that I want to be, well, I permit myself to be away from V1, but the farthest away I can be is 10 units. Okay? So it simply tells you that you can go 1 unit here, and then 1 unit here. I'm still within 10 units of distance. I can go, what was it, 3 this way. And how much was this? 3 again this way, because I'm still within 10 units. Now that's 4. I can go 6 more units here. That's it. That would be the farthest I can go. Now that simply says that if I want to cover V1 by a point X whose distance is at most 10 units away from me, then my X should be in this cross-hatched portion of the network. It cannot be over here. Okay? So now this time, of course, we again have a radius, but the center is V1. So you have a center at V1, center meaning not the center, absolute center we're looking for, but just think of it as if you're doing a circle. So you place yourself at V1 and you go a radius of 10 units every which way on the tree. Okay? And you do the same thing for other vertices. So for each vertex, you have one such subtree. And if you want to find a feasible point that satisfies all of the constraints here, then those subtrees must intersect at a point, or at more than one point if possible. Okay? So as long as you find the intersection of all those subtrees, you are in a position to pick one of them. And if it turns out that you can also reduce the value of z slightly or more and still have a non-empty intersection, you will be in good position. Okay? That's what you're looking for. All right, so these things require some geometrical viewpoints. That's the idea. Once you get the geometric idea, then, of course, you can work out the algebra of it. Except that networks are not like Euclidean spaces, so you need some additional notions to work with, which we've actually built the basis for. All right, so you got the idea here. So x bar is the midpoint of any longest path in T connecting some two vertices. True in general for any tree network. Not only for this example.
I think we can also relate that AIs are zero. We know that the longest path will be from a leaf node to a leaf node.
That's
so
right.
We can add those AIs to those leaf nodes.
I was going to get into that later, but don't go ahead of me. Yes?
So the solution is found intersection of the longest paths. This is actually true without the special case as well.
For general networks,
No, I mean,
you still have the same situation. Okay, let me put it this way. Now, the viewpoint I gave you, where you take each vertex and try to move away from it as much as you're permitted to by the upper bound. Okay? So if you think of the same problem stated in the form of distance constraints of this kind, with x this time varying in the network rather than in the tree, the same viewpoint is still valid, meaning that you define a subnetwork associated with vertex I, which consists of all points in the network, and of course this is relative to a particular value of z. Okay, let me write it this way. So you pick a value for z, a positive number, and for the ith vertex you define this set whose distance from vertex vi is less than or equal to that z, only for one vertex. Okay. Now, because of the continuity of the distance function, for fixed vertex vi, this function is continuous, and so it will start forming a subnetwork in the entire network, okay, which is coverable within a distance of z. And what you want is, you want these subnetworks to intersect, to have non-empty intersection. And so the problem can be stated this way. Find the smallest z such that this intersection is non-empty. Okay? Now, that geometric viewpoint is still valid, if I think that's what you were asking. And, however, for the case of general networks, the algebra is a bit more difficult. Well, actually, it was worked out, but it's not as clean as the tree network case. For the tree network case, if you assume all addends are 0 and the weights are 1, it turns out that it amounts to finding a longest path in the tree and taking the midpoint of it as your minimizer.
I was asking about that. We take weights as 1 and atoms as 0, and we find that approach. And you say that true in general for any tree network. So this approach works if...
As long as the special case holds.
Okay.
Yeah, I'm still under this special case. Okay, all weights are 1 and addends are 0, except that we'll make it slightly more general by doing what you just suggested. So, why is it true for this special case when weights are unity and addends are 0? Because, of course, the subtree associated with one end of a longest path and the other end of a longest path, when you take z to be the radius or the half of that particular path length, then they will intersect at a unique point, and you cannot move anyway. Okay? And that's why it's true. Okay? But the viewpoint is, I think, quite general, and you should actually make use of it whenever you work on such problems. So you might want to ask yourself, well, how am I going to find the longest path in a tree network? Well, if the tree is small enough to process the information by inspection, you can do it by eye, just by eyeing, just by inspection. Otherwise, what you can do is pick an arbitrary vertex, say VA, whatever A is, find a vertex VB farthest from VA, meaning that you simply compute the distance from VA to VI for every, well, you've got these distances on the side, you maximize over I. Okay, the output of this happens to be some vertex which you call VB. Next, find a vertex VC which might be VA farthest from VB. The path connecting VB and VC is a longest path. And its midpoint is your minimizer for the absolute center problem. This is suggested by Handler and proved by Handler. Well, I think it was 1972. Could be before that, actually. I'm not exactly sure now. Let me see if it's in my notes. I don't have it with my notes, but nevertheless, it's a rather simple way of doing the job, okay? So in the previous example, I don't know, suppose you picked, for example, this one as your VA. When you find the farthest vertex from here, 3 plus 6, that's 9, plus 15 is 14. So this will be your VB, or this could be also your VB. And then you find the farthest from this one, 5, 6, 3, 2. So that's going to be your VC. And that will be the longest path, okay? How do you prove it? Well, you might want to work on it at home, okay? These are things you should be able to work out on your own after a while. Okay. Let's take a 10-minute break and then we'll continue.